Okay, questions 4 through 9. Here we have a rod with attached mass m, so here's my attached mass m down here, is free to rotate about its pivot point. A particle with velocity v and mass m/2 collides and sticks to the free end of the rod. Find the angular momentum of the system just before collision, and the rod's mass is negligible. Okay, so this object is the only thing that's moving right now, and you might be inclined to say that there's no angular momentum, but don't say that, because this rod is rotating and this will rotate, and this object becomes part of the system. So this gives this whole system initial angular momentum. When it collides, it'll stick to the end of this rod and it'll pivot. So let's use the relationship between linear and angular momentum. Angular momentum L equals linear momentum cross R, or linear momentum times R, where the linear momentum is at a 90-degree angle with the moment arm. And indeed that is the case. The velocity going in, here is the moment arm. This whole rod is 2r, so the length of the moment arm is r, half of that. And this is how the momentum is coming at a 90-degree angle to the moment arm, and the length of the moment arm is just r. This mass also is a distance of r from the pivot. Okay, so linear momentum cross r, that's the m/2, that's this object's mass, times its linear velocity times the distance to the moment arm, which is r. And that is the initial angular momentum. Okay, after collision, the particle sticks to the rod and the system rotates with angular velocity omega. Find the angular momentum after collision. So this is, we can use now L equals I times omega. This rod has two masses rotating about, so we need to get the total moment of inertia and then multiply by omega. So the total moment of inertia from the data booklet is sigma mr squared. So this is the sum of m, which is this mass down here, times the distance from the axis of rotation squared, plus m/2 times r squared. 2/2 plus 1/2, this is 3/2 mr squared, and this is the moment of inertia, the angular momentum after collision. Oh, times omega. Don't forget, L equals I times omega, so the angular momentum is 3/2 mr squared times omega. Okay, so number 6 and 7, they're actually the same question, and I meant to take off number 6 because I didn't want to confuse you with V tangential. We'll go into tangents for topic 6. For now, skip this one. I should have just included number 7. It's the same thing, and I had intended to take off tangential, and I left the whole freaking question up. Oh well. Number 7. After a collision, the particle sticks to the rod and the system rotates with angular velocity omega. Find omega in terms of v. So I need to relate this angular velocity with the initial velocity, the linear velocity, and to do that I'm going to take advantage of the conservation of angular momentum. The change in angular momentum of a system is 0, which tells us that L final minus L initial is 0, which tells us that the final angular momentum equals the initial angular momentum. So let me plug in for these halves, for these two sides of the equation. The final angular momentum is 3/2 mr squared times omega, and I set that equal to the initial m/2 times v over r, or times v times r. So 1/2 times m times v times r. My m's cancel, the halves cancel. I'm going to divide by 3. I will divide by r squared, so I'm solving for omega. So in this case, omega equals v over, I divide by 3, divide by r squared by r, so omega equals v over 3 times r. So that's how I rewrote omega in terms of v. Okay, A net torque of 0.023 Newton meters brings the system to a stop after a few revs. If R equals 0.24 meters, V equals 2.7 meters per second, and M equals 0.98 kilograms, find alpha. Well, torque equals I times alpha, yeah? And I have an expression for my total moment of inertia. It was this, m times r squared plus m half times r squared. So this was my moment of inertia, 3/2 mr squared. So the torque, I'm looking for alpha. Torque equals 0.023 Newton meters. Set that equal to the I, the moment of inertia for the system, 3/2, times m, which is 0.98 kilograms, times r squared, 0.24 squared, times alpha. So I'm looking for alpha. Alpha equals 0.023 divided by all this, 1.5 times 0.98 times 0.24 squared. And what do we get? 0.023 over 1.5 times 0.98 times 0.24 squared. And word to the wise, make sure in your calculator you put parentheses, so you tell the calculator to do the order of operations in this order. And for this value, I got an angular acceleration of 0.2716, 0.27, I'll leave this as radians per second squared. Okay, and number 9, a net torque of this same 0.023 Newton meters brings the system to a stop after a few revolutions. If R is this, all that before, find the number of revs. So to do this, I'm going to need to get the angular displacement, and then I can convert this angular displacement to revolutions by dividing by 2 pi. So this is kinematics, rotational kinematics. So I have omega final is 0 rads per second. Omega initial is v over 3r, because this is the initial velocity now for bringing this object to a stop, or for bringing the system to a stop. So omega initial is the velocity, 2.7 divided by 3 times 0.24, make sure parentheses. Angular acceleration we just calculated is 0.27, and we need to find theta, and then once we find theta we can get the revolutions. I'm using the equation from the data booklet. Omega final squared equals omega initial squared plus 2 alpha theta. Okay, so I will get, oops, didn't mean to bump this. Omega final squared is 0 equals, I will calculate omega initial and then square it, 2.7 divided by open parentheses 3 times 0.24, and that gives me 3.75. Squaring that, I get 14.06 rad squared per second squared plus 2 times 0.27 times my unknown theta. Just note that this torque acts to bring it to a stop. So the only way to bring an object to a complete stop would be to have a negative angular acceleration. So I'm going to throw this on here. And really I should have read the problem carefully up before. Note the alpha should be negative because it's bringing it to a stop. Okay, so I'm going to add this to both sides, and I get 14.06 equals 2 times negative, or 2 times a positive 0.27 now, 2 times 0.27, 0.54 theta. Theta equals 14.06 divided by 5.54, and I get 26, about 26 radians. okay? And remember, for every 1 revolution equals 2 pi rad. So I'm going to divide this by 2 pi rad to get the revolutions. So 26 divided by around 6 2 times second pi, and I get 4.14 revs before this thing comes to a stop. Okay, so this question is really great because it's a review of rotational kinematics, and we have now the relationship between linear momentum and angular momentum. A question like this will definitely be on your test. So I hope you found this video helpful. Join me for the next few questions. Thanks for watching.